Nope, you're not writing anything down for the moment. So video game design. When you think about video games, this was one of the original popular video games back when Atari was popular. And we want to talk about how Ms. Pac-Man is moving. So what happens as Ms. Pac-Man works her way around the screen? Just try not to get eaten by ghosts. So she's eating little dots. How's she moving?
90-degree angles.
90-degree angles. What else? Up and down, side to side.
Left or right?
Left and right. Okay, but is that it? Is that all that she's doing?
No. She can move like cross the plane.
So if we look at just left and right and up and down, we're going to look at this particular video, and this is just translations. Left, right, up, and down is a translation. And let's see if we're right. Is she only moving left, right, up, and down? Now, they're going to take away the mouth. The mouth is not going to be opening and closing, but she's going to follow that same path with just translations. And there are no ghosts in this. So here it goes. So is this only left and right and up and down?
Yeah.
It looks weird, doesn't it? A, her mouth's not opening and closing, but is her orientation correct? It's not the same. So she has more than just left, right, up, and down movements. What other kind of movements are we missing?
Chomping.
Obviously the chomping and the sound effects. But she's also not rotating or reflecting. Okay? Thank you. So let's look at her as she's rotating or reflecting. So it's more than just translations. We also need some reflections.
Alright, so everything was never learned in geometry. So they just have to.
All right, so here comes some reflections. Now watch her. Here she goes. Okay, she reflected to go the right way, didn't she? But now what's wrong?
She's not reflecting up.
She's reflecting left and right.
Not up and down.
So it wouldn't be a reflection up or down because then she'd be upside down. What does she need to do?
Upside down and upside up.
She needs to rotate. She needs to pivot. Okay? So let's see how she looks when she pivots.
How do they do this?
Okay, so here we go with translations, reflections, and rotations now. So that looks right. Still not chomping, but at least she's going in the right direction now, right?
Wider.
Rotation, reflection, rotation again.
It's kind of getting like under my eyes.
But does that look more normal?
Yeah.
Except for the chomping?
Yeah.
Okay, now we have to think about being more precise as well. We can't just say moving left and right. We have to give her definite restrictions because we have a maze here, don't we?
Oh yeah, you can only move right or left.
Based on the barriers. So how would we decide if you were a video game designer to help coordinate those barriers? How do you tell her how far to go?
By the dots.
By the dots. So what would help us to be able to count those dots and tell the placement of those dots?
By little boxes.
The coordinate plane, a graph, exactly. So let's look at the coordinate plane and how it would be overlaid on top of it if you were a video game designer. So each one of these dots is now a coordinate on our coordinate plane. I did not make the videos. But I think they do a good job of explaining the types of transformations that we're going to be looking at. translations, rotations, and reflections. Okay?
We watched the regular one because it started hurting.
So, got a notes sheet for you to take some notes today. So, when a point is translated A units horizontally and B units vertically, gentlemen, when a point is translated A units horizontally and B units vertically, then we are talking about the new image having a value of what?
A plus B.
Not A plus B.
A and B.
X and Y are moving from XY to
Y and X.
moving A units horizontally. Which one's horizontal?
A.
X. So we're moving X plus A and Y plus B. So in your first box in the upper left corner, write that down. X and Y are moving to X plus A, Y plus B. Write that down in the blank. So I'm going to have you translate triangle ABC. Triangle ABC is on your figure in that box. I want you to take that triangle and I want you to translate it 4 units left and 3 units down. So start with point A and move point A 4 units left and 3 units down. Put a dot there and call that A prime. A prime is an A with an accent mark, like a half a quote. So you're moving it 4 units left, 3 units down, putting a dot there and calling that A prime. Now translate B, 4 units left and 3 units down, and call it B prime. Mm-hmm. Then translate C, 4 units left, 3 units down, and call it C prime. Then connect the dots, and then tell me what the coordinates are of the new points, A prime, B prime, and C prime. In the very little spot that you have at the bottom of there, tell me what those new coordinates are.
A prime is -4.
Good, right? A prime, parentheses, -4, comma, 0, in that very little spot that's at the bottom. Then tell me the coordinates of B prime. And then tell me the coordinates of C prime. we should use the notation. Okay. All right. Everybody good? A little accent. Yep. A little, like a half of a quotation mark. Okay. All right. Now, as we move to the next box, that's the one on the right, upper right. So we're going to talk about vectors next. So vectors have both direction and magnitude or size. So write that down in the upper right box of your notes. Vectors have both direction and magnitude or size. This is your words. These are your notes. So write them as they make sense. But magnitude means size. You did learn this in science, so we're overlapping with your science classes. The initial point of this vector is D. How do we distinguish between the initial point and the terminal point? Can someone tell me how you can tell which is which? The arrow. The arrow is at the terminal point. So we name this vector vector DE, always naming it with the initial point first, the terminal point second. And notice the notation here, the symbolism. DE has a half an arrowhead on it. So it's not a ray, it's a vector. Okay, it's just telling you how far to move and in what direction to move. Okay, this is the second box, the upper right. Okay, so this vector is named vector DE, and the component form of this vector is -4, 2. And notice that's not an ordered pair. Okay, that is, it looks like a less than symbol and a greater than symbol, but they're actually pointy and they're not as steep or steeper. So -4, 2 is the component form of vector DE. Why -4, 2? Good. It's going which direction? What's -4? It's going left, -4, and up 2. So 4 units left, 2 units up, has a component form of -4, 2. Okay, everybody's got that? All right, next slide. These are vectors in real life. Okay? Vectors are nothing more than something telling you where something has moved. So when you see the vapor trails of a jet, it tells you where that jet's been and in the direction it's going. When you're looking at the tread marks of a peel out of some tires, tells you where they started and where they ended up. When you're looking at playing pool and you want to hit the ball in a way that's going to make it go into the pocket, vectors. Same thing with baseball. When they show you where they've hit that pitcher and which direction the ball has gone, those are vectors. And likewise, when you're seeing Madden or what have you, telling you where these guys are running or where they've been, where they came from, that's also vectors. Yes, sir. Okay. So, next slide, I want you to write the vectors, name the vectors, and then write their component forms. So when we're naming vectors, we have to be careful. We always want to start with the initial point and the terminal point. So locate your arrows. Yes, sir. Nope. Those pictures, you didn't have to write anything down. Okay? That was just some examples of vectors in real life. So now when we're looking at these, Your graphs are very tiny. So can everyone see where the arrows are? Okay, identify the arrows. I'll enlarge them here. Everyone see the arrows? So make sure you name them correctly. Initial point, terminal point, and it's not a ray. Use the vector mark. Mm-hmm. We'll come back to it. Okay? Mm-hmm. All right, so you're in the third box, and you're telling me, so we are writing down the vectors, and we're writing down the component forms. So why did I name it JK and not KJ? Starts at A, J moves to K. That's the initial point. Terminal point is the same as an end point. Yep. Okay. All right, check yourself. Do you have the same thing I have? You have the same thing I have? Okay, next slide. Translation moves every point in the figure the same distance and the same direction. Okay, so you start with your beginning point, F to G, and then you ask yourself how many units right, how many units up. Positive 2, yep. Okay. You guys are talking, I think that you're done, so I keep moving on. Half an arrow, yep. It's not a ray, it's a vector. All right, so a translation moves every point in the figure the same distance and the same direction. We're in our fourth box now. Write this down. The original image is called the pre-image. And it's the image before we move anywhere. The resulting image is called the image. Okay, writing this down here. In the third box, or fourth box. What's on the... So a translation moves every point in the figure the same distance and the same direction. Your original image is called the pre-image. And after the movement, it's called the image. So we've moved NO, segment NO, to segment N prime O prime. And the thing to be aware of is that the distance between O and O prime is equal to the distance between N and N prime. And if you draw a segment between O and O prime, it's going to be parallel to N and N prime. Same slope. And it will also be the same length. Okay. They'll be here. If I catch them, they'll be here after school for an hour. Okay? So if they move and move along the same track, it's possible that they'll be collinear. Okay? Everybody good? So your translation is moving everything from one point, or every point from one place to the new location, same distance, same direction. Pre-image, image. If you can remember that they're either going to be parallel, or if we decide to translate this maybe in this direction, my new O prime could be here, my N prime will be down here. It would be collinear with the original, wouldn't it? Same length, same distance, same direction, but now they're collinear. Okay? Okay. Everybody good? All right, next slide. Need a little more time? Sorry. Take it back. People who throw markers don't need to have a drink.
I didn't even throw the marker.
Okay. Everybody good? No? Okay, on the next one, you're going to need to put axes for me. Okay? So you just have a grid. We need to have axis at 3 units in and 3 units up. So draw the axis, x and y axes. And I want you to write the vertices of triangle ABC. We have A at 0, 3, B at 2, 4, and C at 1, 0. So make sure you label them. Probably Saturday. Once you have them, I want you to translate triangle ABC using the vector -1, -2. So plot those 3 points. You're going to have to put an axis there because there's not one there. Okay. Perfect. Once you have your pre-image, I want you to make your new image, which is using the vector -1, -2. What does the vector -1, -2 mean? Left 1, down 2. So take every point, move it left 1 and down 2. Label those points A prime, B prime, and C prime. So there are my original 3 points. So there are my original 3 points. Here are my 3 new points. There's A prime, B prime, and C prime. If it helps you to connect the dots first, feel free, but if it helps you to not connect the dots and move them, it's up to you. But make sure you label those vertices. So here's my initial triangle. Here's my new triangle. Your butt out. Everybody good? Most people know when to stop. Next one. We have 3 points, A, B, and C. This time we're not graphing. Okay? This time we're not graphing. We're going to write the component form of the vector that could be used to translate A, B, and C to A prime, B prime, and C prime. So we had some vector that was a rule that moved these things to their new locations. Okay? What is that vector?
Vector is. Oh, that's the one that moves it, right?
Mm-hmm.
So it'd be -1, -2, right?
Nope. So what happened with my x coordinates? I went from 1 to -3.
-4, -1.
So -4 is the possibility here. Let's check the b primes. Does 7 to 3 use vector -4?
Yeah.
And how about 4 to 0?
Yeah.
Okay, it works. Now let's think about what happens with those y values. It went from 1 to -1. That's -2, 2 in the down direction. Then 3 to 1 is 2 down, and 8 to 6 is 2 down. Okay? That's vector notation. That's component notation. And I think you'll like it better when you see what coordinate notation looks like. Coordinate notation says I'm mapping x and y to a new location. Okay. Mapping x and y to a new location. Where are we mapping it?
-4, -6.
X is now going to become x minus 4, and y is now going to become y minus 2. Okay, that's also known as writing a rule. Writing a rule for a translation. If someone asks you to write a rule for a translation, they want the coordinate form. Coordinate notation. Which one has more writing? Component form or coordinate form? Definitely coordinate notation. There's a lot more writing with it because you write parentheses x comma y and then an arrow to say mapping to parentheses x minus 4 comma y minus 2. There's a lot less writing in component form. Okay? All right. Here we go. We want to take points A, B, and C, and we want to map those translations. So A is at -3, 4. Plot it, label it. Then B is at -5, 1. Plot it and label it. And C is at -1, 0. Plot that and label it. They are tiny. Now we want to map that translation using a coordinate notation. We're going to say, let's take x and y and map it to x plus 4, y plus 6. So move them which way? Over 4 and up 6. So take every point, take A and go 4 to the right and 6 up, and draw an A prime there. Then take B and move it 4 to the right and 6 up, and label that B prime. Then take C and move it 4 to the right and 6 up. Label that C prime. Now we want to take that original 3 points, A, B, and C, and we're going to map those using the vector notation, the component notation of -2, 4. What does that mean? Over which way? -2 means left 2. 4 means up 4. So take your original A, move it left 2, up 4. Shouldn't be. Your original point. Not your new one, your original. Take your original and go left 2 and up 4. Plot that point. Call it A double prime. A double prime. A with 2 tick marks up there, 2 quotes. Then take B, the original B, and move it 2 to the left and 4 up. Call it B double prime. That's okay. And then move C 2 to the left and 4 up. Call it C double prime. One more translation. Take your original triangle ABC and move it which way? 2 to the right and 7 down. So take the original A, B, and C, move them 2 to the right, 7 down. That's okay. Sometimes they overlap. Just put a little, make sure you just note that they're both there. Label them both. It is. Yep, now we're going to call them triple prime. A triple prime, B triple prime, C triple prime.
All right, then it goes off the paper.
Shouldn't. Because we're always mapping the original.
I know, it gets off the paper.
Oh.
Alright, so you start here. 1, 2, 3, 4, 5, 6, 7.
Mm-hmm.
And right here, there. I must have done it wrong. Oh, I'll just.
Okay. All right, so let's talk about rigid motion and isometry. Rigid motion, second from the last box. Rigid motion is a transformation that preserves the length and the angle measures. Another name for rigid motion is isometry. So you basically start with whatever you start with is what you end up with. Your pre-image and your image are going to be the same. Okay? Your pre-image and your image will be the same when it's all said and done. Composition of transformations is when two or more transformations are combined into a single transformation. Well, it doesn't make sense with Ms. Pac-Man, would it? Because we wouldn't want her to be able to go through the maze. But there are times when you want to be able to transform once, transform a second time, and to figure out what the net result was. Yep. So rigid motion preserves length and angle measure. Well, it's in the heading, so you could realize that that's going to be the same. Okay. And then the second one, when two or more transformations are combined into a single transformation, is a composition. Okay. We have a theorem here that says that it's called the composition theorem, and the composition of two or more rigid transformations is called a rigid motion. And what they're meaning is that it doesn't change size or shape. It preserves its size, shape, angle measures, and so on. So whatever triangle or hexagon or Pac-Man figure you started out with is what you're going to end up with at the end. Mm-hmm. The composition of them. Okay? If we start with one and then add another one onto it, the result will still be a rigid motion. We're not stretching anything or making it smaller. It's going to preserve the size and shape. Okay, one last example. That's a composition example. Composition example is going to be talking about how do we compose two of these motions together. I don't have time. Are we ready? All right, so last slide. So we want to know what the composition of this image is going to be after its translation. So we're not looking at wanting to do two separate translations here. Okay, what's the original going to be, the pre-image, and what's the end result going to be?
All right, so we put down -8, 5, then -6, 8. Right?
So I want you to graph segment RS. Okay, graph segment RS. This is just a segment, so it's just going to be 2 points with a segment in between. Okay, not even as complex as a triangle right now. We're just looking at a segment. So segment RS, R has the point -8, 5, and S has the point -6, 8. Everybody got RS plotted? -8, 5, -6, 8. Okay, now if I do two transformations with it, one of them that is moving it What does x minus 1 mean?
-1.
What does x minus 1 mean?
It moves over one space, -1 space.
Okay. So r was the point -8, 5. S was the point -6, 8. So if I'm going to take those 2 points and I'm going to do a double composition here, okay, I'm going to do a composition. I'm doing a double translation. Okay, it's going 1 to the left and then it's going to go 4 to the right. So take S and go 1 to the left, then move it 4 to the right. Okay? Now take R, and what does the first translation say?
Wait. This translation is 4.
4 up, and then
6 down.
6 down. So we're going to take R and go 4 up, and then go 6 down. Hold on. Wait 1 second. I did my S prime wrong. So S is moving 1 left and 4 right. And then it's moving 4 up and 6 down. There's my new S prime. There's my new S prime.
Alright,
So we're going to do that for R as well.
let's you.
I'll let you do it. And then you can check yourself.
Let's you do it.
We're taking S. We're moving it, first of all, left 1, then right 4. And then we're moving it up 4 and down 6.
Let's do.
That's my result. Okay? Bear with me for 1 more minute. Okay? So if we're moving this, we have R and S. Everybody's good with those, right? R was -8, 5. Okay? So we're at -8, 5, and we're told to move it left 1 and up 4. But then we also have to move it right 4 and down 6. So we're doing 2 of these together and only getting 1 result. So if we take R and we go left 1 and right 4, and then take it up 4 and down 6, that's our new location. Yep. The assignment at the bottom is going to be what you're doing tonight. 7 problems is all. The monitoring part, monitoring progress 1 through 4 on page 175, and 5 through 7 on page 177. If you want to go crazy and do the rest, tomorrow's assignment's listed as well. And then you don't have homework on the weekend. Okay?
Sorry.